Great. All right, so our next speaker is going to be Phil Wadler. Phil is at the University of Edinburgh, and he's going to be telling us about some types of types. Love the title.
Right. Good morning. How many of you are locals from Japan? Okay. And how many of you are jet lagged? Yeah, more or less the complimentary set. Okay, so I need you to work with me. This is going to be an introductory talk. It's following two great introductory talks. I thought Aaron and David both did an amazing job. But I want you to help me, right? My problem is I know this stuff too well. So I will think something is obvious when you don't think it's obvious. So I want you to promise that if you don't understand something, you will ask a question. Will you promise to do that? Thank you. Now, people often get really shy about asking questions, particularly in an environment like this. So if you're sitting in ICFP in a couple of days and somebody starts talking about something and you have no idea what they're on about, here is my secret tip to you. Right? Somebody starts saying something, turn to the person next to you, right, and whisper in their ear, he's talking about monads. What on earth is a monad? And then one of two things will happen, right? The person might say, oh yeah, monads are something they use in Haskell all the time. Everybody knows about those. What's wrong with you? Right? But much more likely, that person is going to say, I don't know, I've never heard of a monad. I've got no idea what's going on. Right? So if there are at least two of you who don't know, there's probably a lot more people in the audience who don't know. So you will be doing everybody a favor if you raise your hand and say, excuse me, sir or madam, for my profound ignorance, but I don't know what a monad is. Could you explain, please? Right? And you'll be helping everybody in the audience and the speaker to do their job properly. So it's your job to ask questions. And of course, you want to make a good impression on everybody here, and asking questions is a great way to do that. So it takes a lot of bravery to ask if you don't understand, but that's what you should do, okay? I'd like you to do that during my talk as well. Brilliant, yes?
I asked Mr. Jones yesterday, I wanted to know the history of this IO monad.
Yes.
And he referred to a paper, and I read it, and I think your name was on it.
Okay.
So do you know about this IO monad?
Okay, so the question is, do I know about the IO monad? And the answer is yes. Is there anything else you'd like to know?
No, just I thought maybe you...
We could discuss that afterwards if you like.
Okay, all right.
Okay, are there any other questions? Right, questions are good. Okay. Right. How many of you have heard about the idea of propositions as types? Ooh, lots of you. Okay. Or it's also sometimes called the Curry-Howard isomorphism. More hands going up. Okay, you will all be bored. Here is, oh, no, I'm not going to do that first, right? So Aaron began by talking about how we use lambda calculus and other things to make models of programming languages, right? And I think he hit the balance exactly right, which is it's very important to have a simple mathematical model. And then it's also very important to think about how does this model fit with reality? Both of those are important. But you really want the model. Okay, there's a great quote from Gerard-Reynolds, writing, I think, in the 1600s, and he said, if you can make a mathematical model of something, I think he says if something is susceptible to a mathematical treatment and you don't use it, then it is as if you are trying to explain a room, explore a room in the dark, and you have a candle available, and you don't use it. Right? You really want those mathematical models. They literally light your way. They're a brilliant, simple thing to go on. So let me show you my favorite mathematical model. Here it is. So this is a fuzzy lambda. So my daughter made this for me, right? She has lots of fuzzy toys. She thought I should have one as well. So this is it. And the main point of this is to point out that, well, A, they're small and simple, but this is how you should think of models, right? People think of models as hard. Like, I also have a lambda statue made of metal, right? And that's hard. You wouldn't want to cuddle it, right? This is the right way to think of it, right? Models are your cuddly friends. And that's how you should be thinking of having a nice, simple model for things. You also want a nice, simple model for things, right? This is where taste comes in. And there's a real problem here, which is everybody in this room is much more clever than I am. Right? You're all really smart, and you can all deal with really complicated models. So like Amal comes up with these incredible step-indexed models, or Derek Dreyer comes up with these incredible step-indexed models, and they are brilliant, and I can't follow them. So you will all come up with great models, and after you've come up with a great model, your next step is, how can I make this as simple as possible? And then once you've done that, try to make it simpler again. Right? I've got some papers I've written recently where I said, I did this model 10 years ago, and I thought it was great, and I went back and looked at it 5 years ago, and I couldn't understand a damn thing I did. So here's a simpler model that I think I could understand 5 years later. Right? So this is me urging you. I know you're all very clever, and that means you are all capable of doing this immensely sophisticated models, and of course you should go off and do them. But once you've done them, please, for my sake, think about how to make them simpler. That's the best way to communicate. Make things as simple as possible. Even thinking about things like, what alphabet do I use, can help the communication. And people like Tony Hoare, you will find he writes it all out longhand and then goes back to it later and rewrites it, making it as simple as possible, and then goes back to it a month later and rewrites it, making it as simple as possible. That's how you do it. Tony Hoare's degree, by the way, is in classics. I explained this once to my friend who was one of the first employees at Microsoft, and he thought about it for a minute and he went, well, that makes sense. That's what he writes. And the reason I'm whittering on about this is you guys are at the beginning of your career, but this is what you're going to do. Somebody in this room will come up with a model as simple as lambda calculus, as simple as pi calculus, and as profound and as useful, and that is your job. That's what I'm expecting all of you to do. And that's why it's a great privilege for me to come up here and show you now the coolest model, propositions as types. And one thing that makes these cool is, right, they didn't just come along with the computer. They came along a bit before, with the development of formal logic in the 1800s and 1900s. So let's go back to 1935, and Gerhard Gentzen invented all of modern logic, right? And this is amazing. Sad to say, he was also an anti-Semite and a Nazi. So that those aspects of him are not so great, but his science is wonderful, and we do need to learn to distinguish the personal from the science. So here is what he wrote. This was basically his doctoral thesis. This is something you can all aspire to. So this is the formulation of logic that we use today, natural deduction. Formal logic had come in with Boole in the 1800s, and it takes a while, right? So 50 years after Boole first comes along, you get Frege, and then Frege after 50 years after Frege comes along, you get Gentzen. So 100 years, we finally get the one we're using today. And we're still using it close to 100 years later, 85 years later. So here it is. I'm going to show you just a fragment of it. This is, by the way, exactly what's written here. The implication part is this bit here, and the and part is that bit up at the top. And it's exactly identical. Yes? Oh, well, that's much easier. Thank you. Oh, I can pretend to be a stand-up comic now. Great. So it's exactly the same, except I've written some stuff in blue, and I've written my letters in English rather than in German. But other than that, it's identical. So how many people have seen this sort of thing before? Yeah, quite a few of you. Great. I'm going to bore you by explaining it anyway. So let's begin by looking at conjunction, the rules with and. So here's the really key insight that Gentzen had. And understand, very clever people like Hilbert had been doing this before, or Russell, and they hadn't had this insight. So if you look at Hilbert's formulation of logic, it's very different. And Gentzen had this key insight, which is the rules come in pairs. So they're in natural deduction, they're introduction and elimination pairs. The very same paper also introduces the other main way of formalizing logic, which is called sequent calculus, where the rules also come in pairs, but they are left-right pairs. And the point of having the pairs is, so an introduction rule says, here's how we introduce, create an and. When are we allowed to conclude that A and B has been proved? We're allowed to conclude it if we have a proof of A and a proof of B. Of course, these are exactly the inference rules that David was showing you in the previous lecture. So if you have a proof of A and a proof of B, you can conclude A and B. And then how do we use such a proof? Well, that's an elimination. You have an and above, and you get rid of it below. And there are two ways we can do it, right? From A and B, we can conclude A, but also from A and B, we can conclude B. And then the other rule says, okay, under what conditions can we conclude that A implies B? And the answer is you assume A, and if assuming A you can prove B, then you know A implies B. So there's little brackets around the A says we are assuming A. And you notice I've linked the rule to the assumption. So that says this rule has been discharged by this assumption. Sorry, this assumption, got that backwards. This assumption has been discharged by this rule. And then how do you use it? Well, you can say if A implies B, and if I have a proof that A implies B, and I also have a proof of A, then hey, I can conclude B, because I know A and I know A implies B. So I've got a proof of B. And that rule is called implication elimination, and that's very old. It goes back to the ancient Greeks, although it was given a name in the Middle Ages where it was called modus ponens. Okay. So the rules come in pairs. Introduction rules tell you how to create a given connective, and elimination rules tell you how to get rid of that connective. So let's look at a simple proof. I'm going to prove that B and A implies A and B. Wait, of course, it's and. The order doesn't matter. Of course B and A implies A and B. How is there even anything to prove here? Well, right, but we're doing it formally, and the formal rules don't say anything about that. So does it follow from the formal rules I just gave that B and A implies A and B? You know, that's something, it better follow from the rules. Okay, so how do we prove it? Well, we're doing an implication, so let's assume B and A, and notice the assumption occurs twice in the proof, and both uses of the assumption are discharged by that rule on the bottom. And then we've got, let's see, it's hard to point at the screen. You don't have a pointer, do you? Yes. Right, so it's just an arbitrary name, and it just says this is linked to this, right? And there might be lots of things linked into proof, so we'll need lots of different names. Thank you for the question. Are there any other questions? Thank you, but yeah, it's hard to see, so I'll just do this. We can see this. No, I don't trust pointers. I had one once that was really powerful. I could kill people in the audience with it, but
it's better than nothing, I think.
I can't see it.
Oh, you can?
No, I'm. No, I can't see it. Everybody else can probably see it, but I can't see it. So I'm going to do it this way. Can people see that? Yeah. Okay, good. So here's the assumption, B and A, and we've used it twice. And right from B and A, we can conclude A, right? And from B and A, we can also conclude B. But here's a proof of A and here's a proof of B, so I can conclude A and B, and then I discharge the assumption, so I know B and A implies A and B. And then we've got some rules for simplifying proofs, but instead of talking about the rules in general, let me show you an example. And I'll go back to that. So here's the proof that we just had, right? That B and A implies A and B. And here's some proof of B. Let's not worry about what it is. And here's some proof of A. And from those, we can, of course, conclude B and A. So now I've got a proof of B and A. And now I've got B and A implies A and B. So I can conclude A and B. But, yes, question?
What do you exactly mean when you say discharge the assumption?
What do I mean when I say discharge the assumption? So I simply mean I'm going to write a name next to each of these. Here it's Z. I'll write a name next to this proof rule. And that says this proof rule discharges the assumption. That means it's no longer an assumption of the proof. It means we've discharged it. It's not an assumption that you need to prove anymore. Indeed, right, we don't need to prove it because when we end up using it, it ends up getting proved here. Okay, so it's just a way of saying this isn't an assumption anymore. So every assumption that you make eventually needs to be discharged by some rule. Okay, thank you for the question. That helped clarify why I didn't explain very well. Okay, so here's a long proof, but in fact there's a much simpler proof. So let's simplify the proof. So this was Gentzen's insight. The reason we break things up into introduction and elimination rules is that if you end up introducing something and then eliminating it immediately, you can simplify the proof. So here we introduce and then immediately eliminate B and A implies A and B. So let's do another proof that doesn't have this formula in it. And what we're going to do is we're saying, well, here we've assumed B and A, but here we have a proof of B and A. So let's just take every place that the assumption appears and replace it by this proof. So now if you look, you see you get this. Notice this proof could be really big. So we might actually, by doing this simplification, we might be making the proof bigger, but we will be making it simpler. Okay? And we know it's simpler in that we've gotten rid of one formula. And notice that when we copy this on top of here, well, these are and E rules, and this is an and I rule. So now we've got two places where we have an and I on top of an and E. And so we can simplify that, right? And how do we do that? Well, here I've got proofs of B and A, and then I've got B and A, and then from that I can conclude A. Oh, wait, the simpler thing is to just use the proof directly, right? So we'll do that. Oh, and there's a simple proof of A and B from these two assumptions we have here. Notice I've written these y and x's next to them, but there's no actual rule that has a y and x, so these have not been discharged. Right, so now I can go back and show you that, whoops, the general form of simplification. So this just says this, assuming A, I prove B, and then I get A implies B. And here I've got a proof of A, and then from these two I get a proof of B. A simpler way to get a proof of B without using this formula is to just replace the assumption of A by the proof of A. And here we just say, well, if I've got proof of A and a proof of B, and then from that I conclude A and B, and then I conclude A. Well, a simpler way is to just use the proof of A directly and ignore the proof of B. Gentzen was interested in this because he wanted to show that you could simplify proofs to eliminate these intermediate formulas. And he proved, using this technique, he showed something called the subformula property. And the subformula property says, I've got a proof. It has a conclusion. It has some undischarged assumptions. I can always simplify the proof so that the only formulas that appear in it are the conclusion, the undischarged assumptions, and any subformulas of these, which means the parts of them. So the subformulas of A and B are the formula itself, and A and B, and the subformulas of A and B. And similarly for implies. Why did he do this? Well, he wanted to show that the system was consistent, that there is no proof of false. And the thing is, if there is a proof of false, there will be a proof of false that only involves a proof of false from no assumptions. There will be a proof of false that involves only false and its subformulas. How many subformulas does false have? None. It's like, what part of no don't you understand? So in this way, he showed there can be no proof of false, because you just look at the proof rules. Nope, there is a proof rule. If we go back to his original proof rules, there is, the way you write false in his system is this funny symbol. So this says if you assume A and you can prove false, then you know not A. And this says if you've got a proof of A and a proof of not A, you can conclude false. That's the law of contradiction. So there is a rule that has false on the bottom. But notice that it's got an A above and a not A above. And these are not subformulas of false. So by simplifying the proof, we could get rid of those. But now after simplifying, we only have false, and there's nothing that could appear above. So there's no direct proof of false. So that's why he was interested in simplifying proofs. Now, at much the same time, that Gentzen was doing this, Alonzo Church was coming up with our friend, the lambda calculus. So lambda calculus was first used as a way of writing down complicated formulas in logic. But the original paper has a wonderful line in it. He mentions at one point, just says, there may be other uses of the system than its use in a logic. But basically what he did, he invented lambda calculus as a way of writing down proofs in a simpler form. It was basically a macro system for writing down proofs. He was inventing macros. But it turned out he had untyped lambda calculus, and it turned out you could write down infinite proofs in that let you prove false and could not be simplified. So it led to an inconsistent system. So to make it consistent, he introduced what were called types. And Russell had done this earlier to get rid of Russell's paradox. So types were introduced as a way of getting rid of paradoxes, of restricting the logic so you could only do valid things. And right, so here's typed lambda calculus. So here's lambda xn, a function from a function. And it says assume x has type A, and then using x we can build up a term n of type B. So lambda xn is a function which accepts an A and returns a B. I'll point here, it's easier. If L is a function from A to B, and M is a term of type A, then of course when you apply L to M, the result will be a term of type B. That's just function application. And Church didn't have this, but I'm going to put it in because it'll make things easier for us to follow. He didn't need pairs because you can actually build pairs up using functions in a complicated way, but I won't cover that. I'll just do pairs directly. So if M is a term of type A and N is a term of type B, then an MN pair is the same, is a pair whose type is A and B. Sometimes we write this as times, A times B. And if L is an AB pair, then first of L is an A, and if L is an AB pair, then second of L is a B. Okay, so here's a very simple program. It takes a BA pair as input, and it returns an AB pair as output. Notice that for AND, right, it's hard to think of the difference between A and B and A. But for pairs, it makes a lot of sense because the ordering is important. And so what's the function going to be? Well, it's accept an argument z and return the second of z paired with the first of z. So it just swaps the order. And how do we know this is well typed? Well, let's assume z has type B and A. Then second of z has type A. And first of z has type B. And then since this has type A and this has type B, if I put them together, I get an AB pair. And then I can discharge my assumption. And now I've got a function with no free variables, lambda z, second of z paired with first of z, whose type is B and A goes to A and B. And those are rules for simplifying things. And the amazing thing is, right, we're all told, right, the halting problem is unsolvable. Right? If you have a sufficiently powerful programming language, you can't know for sure. You have no algorithm that will determine if a program halts or not. But simply typed lambda calculus is very powerful, but you're always assured that things terminate. And so here's our function again. Right? Now let's apply it to some other pair. Let's say it's a yx pair where y is a b and x is an a. So now we've got our function applied to y and x. Let's evaluate that. So this is exactly using the kind of small step operational semantics that Dave showed you in the previous lecture. And we'll just do substitution, right, which he mentioned is a bit tricky to define. And we'll just replace z by our yx pair. So we've just, in place here of z, we've got this yx pair and the proof that it's well typed. And then from the yx pair, we select the second. That would have type, since y has type b, sorry, the second thing will be x, right? X is type A, so the second thing will have type A. So now we've got second here. And again, we've now moved, we're building a pair and then taking it apart, so we can simplify that, right? What's the second of the yx pair? It's just x. What's the first of the yx pair? It's just y. And notice that what we have here is a proof that this term has type A and B, that it's well typed. And as we reduce, we still get valid proofs that the term is well typed. So what we've shown is that as you simplify a proof, it is guaranteed to remain well typed. This is called progress. Sorry, no, it's not. It's called preservation. This is called preservation. As you simplify a term, it remains well typed. And progress says if a term is well typed, it turns out there's always a simplify rule that applies. And then if you know things always terminate, you know eventually that this process comes to an end. So for simply typed, you can show things terminate. By the way, that was first done by Turing. So Turing did the first proof, one of the first proofs that you cannot prove any program halts, but also showed for simply typed lambda calculus that you can show it halts. And by the way, it was Turing who wrote the first paper showing that lambda calculus and Turing machines were equivalent. Right? He went off to work with Church, because Church actually beat Turing to the main result. But Turing's result is the one we remember because he explained very clearly how Turing machines correspond to what people can actually do when they're following an algorithm. Church didn't do that. But Church came up with lambda calculus. And so Turing wrote this paper explaining that the two are equivalent. And in the first line, in the first paragraph, he says, okay, so once we've seen they're equivalent, we know that instead of using Turing machines, we can use the more elegant lambda expressions. So Turing understood very well that functional programming was the right thing to use. And it's just a shame that nobody else understood that at the time. So I've got 15 minutes, right? Okay. Right, and then here are the rules in general. And you can see that this rule is just saying lambda xn applied to m reduces to n with m replacing x, which is exactly the beta rule that David showed you in the previous talk. And then here's a similar reduction rule. It says given an mn pair, if you take the first component of it, you just get m. Similarly for second. Okay. Now, I want you to all reach under your seats. There should be some rose-colored glasses there. You guys did that, right? I guess there's been a mix-up. Apparently you don't have rose-colored glasses under your seat. Okay, but if you did, and you put them on, then of course you would stop seeing the bits in red and just seeing the bits in blue and black. And then things would look very familiar, right? You've already probably worked out that the blue bits here are, of course, the same as the blue bits there. And indeed, right, the proof that logic is consistent, that you can always get rid of subformulas means that this process of simplifying proofs must always terminate. That's part of what you prove. And so the proof that logic is consistent and the proof that terms in simply typed lambda calculus always terminate is the same proof. So this is all completely obvious, right? Okay. It was not obvious at the time. Right? Gentzen, in his original paper, right? Lambda calculus had come out at the same time. He didn't write about lambda calculus. In fact, his proof that you could always normalize things looks very different. I mentioned this other thing, sequent calculus. He introduced sequent calculus just as a way of being able to prove the subformula property, being able to prove that simplification always terminates. So he didn't see this. It wasn't until, I think the year I was born, 1956. This was done in 1935. Simply typed lambda calculus in 1940. Not until 1965, sorry, 25 years later, did Pavitz give this direct style of proof. And then a few years later, Howard finally wrote down this correspondence between simply typed lambda calculus and natural deduction. And it wasn't actually published until 1980 when it appeared in a Festschrift dedicated to Curry. Curry had observed the same idea, but wrote it up in a very complicated way, and Howard wasn't familiar with it. Right? So this is both why you should be familiar with the preceding literature and also why it's really important to make your ideas simple enough that people can follow them. But we do still give credit to Curry, as we should, as well as to Howard. And in fact, many people prefer the name propositions as types to Curry-Howard because there were other people like De Bruyne who also independently saw similar ideas. You can actually go back to the intuitionists like Brouwer and Heiting in the 1920s, and they're talking about similar ideas. So there are many, many origins of this idea. Right, so the way we simplify it is propositions correspond to types, but also then proofs correspond to programs, and also normalization of proofs corresponds to evaluation of programs. So it's right. If it was just propositions as types, it would sort of be the Curry-Howard bijection. But it's not just a one-to-one correspondence. All the structure is preserved. Right? Not just the formulas, but the proofs of the formulas, and then the simplification of the proofs. All of that structure is preserved. And when I first saw this, I wasn't much older than you guys. I thought, oh, that's cute. What a nice little trick. I didn't understand this would be the basis for my research career. Right? And what I didn't understand yet was that it crops up again and again and again. So roughly speaking, for every interesting logic you can name, there is a corresponding simple programming language. And more or less for every simple enough programming language you can name, there's a corresponding logic. And I've sometimes talked about programming languages that are invented versus ones that are discovered. Right? We can say lambda calculus was discovered because essentially the same structure was written down independently twice, once by Church and once by Gentzen. And it took a long time, close to 50 years, before people realized, oh, these two things that these guys wrote down, they're actually the same thing. So it's not just invented, it's discovered. And all of you are very clever. You can invent very clever things. Inventing is a great thing to do, but discovering, I would claim, is even better. So by all means, invent great things, but really, if you can push yourself to discover great things and to capture that discovery in a tiny calculus, that is a real way forward. Okay. And then Aaron has explained the hard work you need to do to turn that tiny discovery back into things people can use. But having that discovery is absolutely essential, right? You couldn't have done Rust without all the theories that underlay it. He's nodding. Okay. So it happens again and again. So, uh-oh, I've unplugged something. This is disaster. It might stop after a while. Right. Let's see. Right. I'll talk a little bit about two specific systems. So there's something called the Hindley-Milner type system, which Robin Milner invented for the ML programming language. That's the way most of us see polymorphism. And Hindley was a logician, and Milner was a computer scientist. There's something else called the polymorphic lambda calculus, which was written down by the computer scientist Girard-Reynolds in 1974. But the computer scientist Jean-Yves Gerhard wrote down the same thing as a logic even a bit earlier. So Curry-Howard is a double-barreled name that guarantees that every good idea will be discovered twice, right? Once by a logician and once by a computer scientist. Right? And in general, it gets discovered by the logician first. So if you read logic, you can get a jump on everybody else. So roughly, right, Curry-Howard is a double-barreled name that guarantees the existence of double-barreled names. Right? Things like Hindley-Milner and like Girard-Reynolds. Interestingly, right, linear logic was sort of only discovered once, and then the different type systems arose from it. By then we understood you could mine the logic to get good ideas. But like session types, which were mentioned earlier again by Dave, thanks for setting me up so well, because there's something I work on now, because of the correspondence between session types and linear logic. And Kohei Honda knew about linear logic, and half the connectives in session types were just stolen from linear logic, but the other half was read and write, and he just put those in, right? So you've got four main connectives in linear logic, and two of them he stole for the two forms of choice, making a choice or offering a choice, which are what the two ends of a channel does. Right? If you're communicating, one end says, well, you can choose between these two things, and then the other end says, yes, I'd like the left one, please. But the other one, right, where one end says, here, I'm sending you an integer, and the other end says, hi, I'm ready to receive an integer. That pairing, he just did ad hoc. Much, much later, Lewis Karras and Frank Fenning, like 20 years later, worked out, oh, actually, input and output, read and write, those correspond to the other two connectives of linear logic. It took 20 years to see it. As soon as they saw it, I went, wow, there's something in logic that tells about concurrency? I'm in there. So that's what I've been doing in my research for the last 5 years. And it's horrible because it means I have to work with people like Nobuko Yoshida, who is like you guys, way too clever. And she comes up with these amazing, really difficult theories. And then I look at them and go, okay, can I do a simpler version of that? And just recently, we took something they called multi-party session types and related it back to linear logic. So we were quite pleased to be able to draw a nice connection there. Okay, I've only got a few minutes. Actually, I could just stop there. Let's see, I'll just briefly mention, right, the fact that you get non-terminating programs, things like lambda XX applied to lambda XX, that actually corresponds to paradoxes in logic. So that corresponds to the idea if you have an infinite formula of the form X, which is the same as X implies X, that is A is implied by A, is implied by A, and so on, an infinite formula, you can prove any A as long as you can write down a formula like that. Here's the proof. It's very short. And that can actually be used as the basis for the fixed point combinator that we use. So Curry-Howard propositions as types is so fertile that even something like paradox gives rise to useful ideas. I'm going to skip that because we don't have time, but you can read that. I want to say just a word about Girard-Reynolds and Hindley-Milner. So here's the Girard-Reynolds system. So this goes to the idea that, okay, we can have quantifiers like for all and there exists, and we'll have a for all quantifier where for all ranges over types. So for every type, we can have a formula of this kind. So in logic, right, types correspond to propositions. This says for every formula of the logic, this might be true. So you can say things like, for every x, x implies x. Okay, yeah, that makes sense. But that corresponds to the identity function that works at any type. So these two rules we saw before, and then these are the other rules. So just if you write big lambda x, that's just for all x, and that just corresponds to, okay, we've got a variable big X whose type is itself, it ranges over types. And so we can now use big X in this formula B. It's bound in there, and it's bound within N as well if we needed to use it. And then we can apply for all xb at the type A, gives us the formula B with X replaced by A. So now we're doing our beta reduction in the typing system. And this is a very powerful system. As I mentioned, it was discovered independently by a logician and a computer scientist. And here's a big word that you'll sometimes see, impredicative. So the first 5 times I heard this word, I ran screaming from the room. But actually, it's very simple. All it means is here, when we've got X, what types is X ranging over? All types, including this type itself. So for instance, the identity function has type for all x, x arrow x. It can be applied to any x. You can actually write the identity function instantiated at the type of the identity function and then apply it to the identity function. That works. So you've got a thing applied to itself. If you know about paradoxes in logic, you know, wait a minute, this gets us into paradox. But it doesn't, right? So Gerhard proved that doing this was consistent, and he did it by turning it into a programming language, System F, and then showing that things always terminated. And that corresponded to the consistency of the logic. So that's what impredicative means. It just means you have types that can be instantiated to themselves, and that means our normal techniques for using induction don't work. So that's what makes things hard. Now this other system is called predicative, and now we have polymorphic types, where we say for all xs, but x now does not range over itself polymorphic types, but only under monomorphic types, which are things with type variables and implications, but no for alls in them. And that's the trick to getting a type system for ML and for Haskell. And this is where I'm going to finish. So this bit is as before, but now what we're going to do is we're going to limit. So this is the generalization rule, pretty similar to before. But except we don't write the big lambda, it just happens. And when we instantiate, we only instantiate on variables, not on arbitrary terms. And then the one thing that introduces polymorphism is this new construct, let. And by the way, this introducing let as controlling where you do the generalization, that was Milner's idea, not Hindley's. And so if M, notice the difference is we have an S here rather than an A. So it ranges over type schemes, things that might have for alls, rather than over monotypes, types that do not have for alls. So we bind M to an S, and then X has this type, and then X gets instantiated automatically everywhere we use it within N. And again, Aaron's talk is a great setup for this. He says, you know, you might do a nice theory, and it might be really powerful. And this is an example of such a thing. And it is really powerful, but we don't write programs that way. And if we did, we would have to have lots of types in the middle of our program. I'm instantiating map at this type before I use it. And it just gets really painful. So Milner's insight was that if you just restrict where you do the generalization, that then all of a sudden you don't need to explicitly instantiate the types. You can always, using techniques from logic, unification, work out the most general type. So that was a brilliant insight. Notice, by the way, that he did it without understanding how deeply it was connected to logic. The very first paper, he doesn't write an upside down A for generalization. he writes a different symbol. I believe it's a triangle, a delta. And it's not until 5 years later that he writes a paper with his student Demas. Then he has understood it's a for all. And indeed, if you look at Reynolds' original work, he uses a triangle as well, not a for all. And it's not until 10 years later that the connection to logic has begun to be understood. Okay, we're done. And what have you learned? Right, you've learned that when you have a difficult job to do, that this is a job for lambda calculus. So I'll stop there. Thank you very much.
Let's take a couple of questions before we go to lunch.
So there were a couple of really great questions during the talk, but only a couple. You guys let me down. So now's your time to make up for it.
Yeah, can you first, thanks for the talk. Can you give us some words about the relation to logic with dependent types?
Right. By the way, you should always repeat a question when you're asked, not least because it gives you time to think of the answer. So the question was, thank you for the talk. Thank you. And then can you explain about the connection to dependent types? I think there's a talk about dependent types later today. Is that right? Right. But just to give you a little bit about it, so I mentioned Howard's work, right? And it was Howard who both wrote down the correspondence to simply typed lambda calculus that I showed you. And then he said, well, wait a minute, we've got these other things in logic called quantifiers. What on the lambda calculus side, on the programming language side, would correspond to the quantifiers, and that turned out to be a dependent typing system. So he came up with the ideas of dependent types by looking at the connections with logic. So this whole insight in a connection between logic on the one hand and programming languages on the other hand directly led to the idea of dependent types.
Talk a lot about programmers or computer scientists looking at logic work and then taking ideas from there. So are there cases where computer scientists need a new logic and they just make stuff work and they work?
So could you just say that a little again? I had trouble.
Okay, so you talk about one way. So logicians think their work first. So and computer scientists look at their work and then use their idea for their need. So is there sort of like a call by need where computer scientists think that if there were to be this new logic, it would be great. So they started thinking and made a new application for their purpose.
Right, so the question pointed out that I've talked about traffic mainly going one way. The logic comes first, and then the computer scientists exploit it. And then sometimes what we have is logicians do something and computer scientists do something, and then they discover that they're the same thing. And what your question was is, well, does it ever happen that a computer scientist has done something and said, hey, there must be a great logic here. And then a wonderful logic has been discovered by extracting it from some existing bit of computer science. That was your question, right? No. That's never happened yet. So that's one thing that you guys might come up with. So I think we're going to finish, right? But I wanted to just leave you with this. You guys are going to go off and write some amazing papers. Some of them are going to have really deep insights about the connections between logic and computing, about this idea of simple models that can guide what we need to do in the world, right? There's so many things, Aaron was talking about some of them, that we need done, that we need to have simple, clear models for. And you guys are going to come up with them. And I'm really looking forward to reading it when you do. Thank you.